In the early days of the railroad, train rails were made of either cast iron or wrought iron. Cast iron was too brittle and would break easily. Wrought iron was too soft and would wear out too quickly. So steel eventually became and remained the train rail metal of choice. The train wheel's rim runs on the inside of the rail to keep the train on the track. This plant makes train rails entirely out of recycled steel, from scrap yards, food cans, and recycled pieces from the rail-making process itself. Electromagnets pick up the scrap and dump it in a charging bucket. A truck hauls the bucket inside, where a crane drops the contents into a furnace. An intense electric current melts the scrap steel at 3,000 degrees Fahrenheit. It then flows into a large brick-lined ladle, where they add carbon, manganese, and other elements to make the steel more durable. The alloy then runs down a ceramic tube that shields it from exposure to oxygen, which would ruin the metal. From there, the molten metal flows into molds, which extrude it into continuous rectangular blocks called blooms. Acetylene torches cut each bloom into 12-foot lengths. A crane then transfers the blooms to a furnace, which over the next 5 to 7 hours reheats them to 2,300 degrees Fahrenheit. This softens the steel for further shaping. Then the reheated blooms enter a machine called a rolling mill, which elongates each bloom, more than quadrupling its length. A shear then slices the longer, thinner blooms into 4 pieces. The pieces now go into another furnace for reheating. This preps them for the next set of rolling mills, which will gradually form them to the final rail shape. Different railroads used to use different shaped rails, which required changing the train's wheels when passing from one railway to another. By the turn of the 20th century, the T-shaped rail became the industry standard and remains so today. For the final shaping, each steel rail passes several times through 3 consecutive mills. This is what a mill's rollers look like, and here's the standard T-shape to which they form the steel. Next, a saw slices off about 12 inches to square off the ends. The cut-off pieces go back to the scrap yard. The rails, meanwhile, are laid out until they cool to about 930 degrees Fahrenheit. Then, an electromagnet piles them in a holding box, where they sit for 10 hours until they cool off to about 190 degrees Fahrenheit. When they come out of the box, they run through 2 sets of rollers. The first set flexes the rail vertically. The second horizontally. This flexing process straightens out the rails, which curve slightly due to all that heating, shaping, and cooling. Next, each rail passes over a mirror, enabling inspectors to examine the bottom as well as the top. Finally, a saw cuts the rails to whatever size the railway ordered, most often the standard length of 82 feet. The Quality Control Department measures random samples to make sure all the dimensions are precise. Every rail bears a number identifying the batch of steel from which it came. In the event of a problem, that number lets them trace all the rails made from the same batch. It's a system that ensures a safe, smooth ride. Desalination plants remove salt from seawater, converting it into fresh water suitable for human consumption. There are more than 13,000 desalination plants worldwide, producing 12 billion gallons of water a day. The desalination plant that produced this drinkable water is located right next to an electrical power plant, which uses seawater to cool down its condensers. Post-cooling, the water travels via underground pipes to the desalination plant. Before salt extraction, the water is pre-treated in a multi-phase cleaning process. First, the water flows through screens that filter out large debris. From there, it flows into basins for the first pre-treatment stage. As large paddles agitate the water, the plant adds two chemicals: sodium hypochlorite, a disinfectant, and ferric chloride, a coagulant. The coagulant binds together sand and other tiny particles of debris, forming heavier clumps that sink to the bottom. This removes a significant portion of dirt from the water, but it's still far from being crystal clear. The water now moves into another set of basins for the second pre-treatment phase: sand filtering. Inside each sand filter, regulated by various pressure and flow gauges, a steady stream of air continually moves sand in a circular motion. The seawater enters at the bottom of each filter and flows to the top. As the sand moves downward against the rising water, the dirt particles attach to the sand. The seawater now looks clean, but still contains microscopic particles. So it enters the final pre-treatment phase. This time, the filtering medium is diatomaceous earth, a powdered rock that contains algae fossils. Finer than sand, it filters out those microscopic particles. The seawater is now perfectly clean and ready for salt extraction. They do that using membranes, cylinders containing layers of plastic sheets that have pores 1/1000th the diameter of a human hair, small enough to trap microscopic salt crystals. The plant pumps the clean salt water under extremely high pressure through long tubes, each of which contains 8 membranes. By the time the water passes through all the membranes and reaches the center of a tube, it's completely salt-free. Plant personnel and a slew of sophisticated instruments continually monitor every one of the system's 10,000 membranes. Meanwhile, the plant sends the debris removed earlier to large waste basins for another round of chemical treatment. After the solids settle to the bottom, the dirty water goes back to the front of the plant to be cleaned and recycled. Pressure rollers squeeze the remaining water out of the solids. Trucks then transport the dry solids to a landfill. The extracted salt, meanwhile, goes to the power plant, which dilutes it, then returns it to the sea in a way that doesn't upset the water's natural salinity level. Processing salt water into fresh water strips away the water's natural minerals. Not replacing them would create 2 problems. First, the water wouldn't taste right. Second, it would damage metal pipes by aggressively trying to replace the missing minerals. Therefore, the plant adds liquid lime and carbon dioxide to the water. These 2 elements adjust the pH level and raise the alkalinity, restoring the minerals and natural taste. Parquetry was invented in France in the 1600s as an alternative to high-maintenance marble flooring. It's made from small pieces of wood bonded together in a geometric pattern. The most common motif is squares, but it also comes in other patterns, such as herringbone, lozenges, and triangles. Parquetry can be made of laminate or plywood. However, the best quality flooring is made from genuine wood such as oak, maple, or yellow birch. The factory first cuts the wood into planks, measuring 2 to 5 inches wide by about a yard long. A drum saw then cuts each plank into 6 blocks about 6 inches long, while an inspector discards any misshapen ones. The blocks then move through a planer that shaves a fine layer off both sides. This reduces the blocks to a thickness of just under an inch and smooths the top and bottom surfaces. Next, the blocks run through a saw with 10 blades that slice them into strips measuring 0.3 inches wide by 6.2 inches long. Quality controllers remove any strips with inconsistent thickness, which are usually the ones cut from the block's extremities. The good strips continue on to another area, where they undergo a more thorough quality control inspection. A worker checks the tops and bottoms, then lines them up on a conveyor belt, good side up. She also discards any substandard strips that may have slipped past the first inspection. The conveyor belt then flips the strips over. This positions the strip's underside facing upward. Saws then cut 2 parallel grooves through them. These grooves are set 0.9 inches in from the edge and are just deep enough to hold a thin aluminum wire that'll connect strips together to form tiles. The next machine dispenses the parallel wires. A wheel pushes the wires deep inside the respective grooves. After every 7 strips, the machine cuts the wires and starts new ones. The 7 linked strips form a 6-inch square tile. An end matching machine now squares each tile so that the 4 corners are precisely 90 degrees. Then it carves tongues on 2 of the tile's edges and grooves into the other 2. 4 tile feeders then drop tiles into an assembly machine that inserts the tongues into the grooves. The machine then applies hot glue, which bonds the 4 tiles into one larger tile measuring 12 by 12 inches. The tiles are now ready for varnishing. Feeders drop them onto the automated varnishing line. The tile surface gets a sanding. Rollers then apply an even coat of varnish. From there, the tiles immediately pass under ultraviolet light. This dries the varnish within a second. Then the process repeats 3 more times for a total of 4 coats of varnish. Workers then stack them in tens, at the same time doing a final inspection and discarding any tile that has a less than perfect finish. On the packaging line, each stack gets a label and clear plastic wrapping. An oven shrinks the plastic tightly around the tiles. Those 4 coats of varnish made this parquetry super durable. And because it's real wood, when the many years of wear do begin to show, you can simply